we've introduced some coordinates x for our Lie group, and then we looked at this combination here and expanded this in the basis of the Lie algebra. And now the claim is, if we take these coefficients of this expansion here, write them in a quadratic matrix, take the determinant and the absolute value of that, and this is a nice weight function for defining our Haar measure here. So we take determinant of this A of x, and then here the dnx is n-dimensional Lebesgue measure. N is the dimension of our Lie group and the dimension of the Lie algebra. And at first sight, all of this looks highly coordinate dependent. It depends on how we parameterized our group in the first place. So first thing we have to check is that it behaves in the right way if you make a change of coordinates. So let's say x is f of y, some other coordinates. And if everything is nice, then if we calculate our Haar measure in these coordinates, we should just get a Jacobian from the change of coordinates from x to y. So let's do this. Let's consider g of f of y, and let's call this g tilde of y. And now we use this instead of the g of x and go through this procedure here again. So what is g tilde of y inverse dg tilde dyj of y? Let's express everything in terms of the original parameterization with the g's here. So we get g of f of x, g of f of y inverse, and then we take the derivative with respect to yj, but all the x's can depend on yj, so we need a sum here. It's a sum over L, let's say, and we have dg dxl evaluated at f of y, and we have to differentiate dfl dyj at y. So chain rule. Okay, this looks familiar. We have this g inverse and dg dx something, so it's just the same as we had up here. So we can express this in terms of the original coefficients a here. We just use this equation up here and write this as I times sum over k and L, k sum from here, L sum from the line before. Now it's xk, and for the pink thing we write a kl at f of y, and then we copy this Jacobian thing here. Okay, but on the other hand, we could have just looked at this one here and said we expand this in the same Lie algebra basis, xk. Let's call the coefficients a tilde kj of y. So the a tilde is just a times this df dy derivative, which will give the Jacobian. So if we now calculate our Haar measure in terms of the y's, what would we do? we would write determinant of a tilde of y, absolute value dny. But that's just the gray thing here. And that's now the determinant of a f of x times determinant dfl dyj at y. So this is really the Jacobian which we expected, and we have dny here. And if we express everything in terms of it was not an f of x, it was an f of y in here. I'm sorry. It's always f of y because that's how we defined it up here. So if we express everything in terms of x again, then let's say here is an x, and this here is the back measure expressed in terms of the x. So everything is consistent. It doesn't depend on which coordinates we choose locally.